All right. Welcome, Nathaniel. Thank you. Today we're going to teach you about what we learned today. And why we're doing it is so that I can always come back to this video. And two, so that it helps me learn it better. So today we learned how to deal with orbital groups and LGOs and what we do with irreducibles and how it affects those groups and how those effects describe the groups. And in order to do that, we're going to go over an exercise, a very simple exercise that can be very difficult overall. So the exercise is simple. What we're going to do is we're going to take CO2 and we are going to find the irreducible descriptions for CO2. Okay, CO2. Now, first thing we need to find is the point group. The point group is the symmetry operations that is capable of, well, everything. One second. Let's edit this so that I can configure video. So that's a little bit more focused. There you go. Okay, the point group. So in order to find the point group, what you're going to have to do is you're going to have to draw the atom first. Okay. Let's see if pencil. Okay, perfect. So the atom is CO2. CO2 is simple. It is a C in the middle with O and O on the sides. Okay, and you don't have to draw the electrons, although electrons can affect the shape of the atom, but as of right now, this is a linear atom, which means that it does not bend due to the electrons, so it's just a straight. So it's just on the X, Y, Z. X, Y, and Z. Okay, well, now that we have our linear atom, we have to figure out what symmetry operations it has, okay? In order to do that, what we do is we put an axis on it. Now, where we put our axis is we could choose, if we're saying it's Z, Y, X, we could do that, but we can change this to have a little bit more effect. We can also say that this is our Z axis with the dot coming out of the page, so it's like this. And we have our X and our Y. Okay, so if it's X and our Y, then what can we do to make this similar to itself? And first off is we can rotate it 180. And that is called a C2 rotation because it is, in order to get that rotation, you'd go pi over 2. And that n is that 2, so that's C2. So if you rotated this, you'd get the same thing. As well as you can rotate, there is an inversion point, I, where it goes over, and it makes an error. If you flip it over itself, it'll be itself again. So that's an inversion point. It also has a rotation here on the x-axis. And that is an infinite amount. So if we have an infinite amount, we know that it has to be of higher symmetry, which means that we have to look at our table. Now, there's only 4 options for higher symmetry. And here they are. We have, one second, D infinite H, C infinite V, OH, and TD. Now, TD has to have 4 ligands. CV, it could be CV, but the thing that separates it is that this has no inversion point, while this does have an inversion point. So thus, this point group must be D infinity. Okay, D infinity, and that is our point group. Okay, that makes things a bit easier, except we can't deal with high symmetry things. Because they have an infinite amount of they have an infinite amount of, well, symmetries. If you see, it goes infinitely down, infinitely to the right. So how do we figure this out? Instead, what we do is we lower our high symmetry to a lower symmetry. And thankfully, this will always be given. So for this question, it is getting lowered to D2H. Okay, so if it's getting lowered to D2H, we just have to go look for D2H. And lo and behold, there is D2H. Okay, so now that we have D2H, we have to figure out the interactions with the central atom, which is kind of easy, but you can also draw, in order to do this, you should just draw it out right away, just to make sure that you know. So, if we have a carbon to oxygen and a carbon to oxygen, there's the first bond, which is always a sigma bond. And the sigma bond is going to look like this. Okay, this is our carbon, this is our oxygen, and this is our oxygen. And you can see that this is the bond that they're making. And that is our single bond. That is the very first bond. You see how there's two bonds here? Single bond. Okay, and that makes things a bit easier. But carbon can have 4 bonds, hence the double bond on both. In order to have double bonds, they're called pi bonds. So here's our sigma bonds, and we want pi bonds. So there's going to be these bonds where they come out of the page. In order to make these bonds, what's going to happen is this is going to go like this is going to go like this, and this is going to go like this, and this is going to go like this. And what happens here is that these, since they're in like the same area, they're going to react with each other like this. And these two, since they both go like an angle like this, they're going to interact like this. In which case, that's how the atoms are formed. That's what we're looking for. So how many sigma bonds are there? There is a 2s, 2p, where there's 1s, 2p, and then this pi bond has 2px. Oh, actually, let's see for a second. I think I drew this wrong. We say this. Oh, that's why. Okay. Sorry, they've set up theirs differently anyways. So either way, they set their x here. So this is going to be 2px and 2py. Okay, so that is 2s, 2p, 2px, 2py, in which case we have 2py's interacting, 2px's interacting, 2p's reacting, and 2s's reacting. And what an s is p's are this, where they look like this, but an s is just a circle. And I know it's weird, but like you already know this, so it's good. It's okay. Anyways, so now we have to figure out how many LGOs and how many atomic orbitals. So carbon by itself has 4 atomic orbitals. And that's with pairing, and that should make sense because there's 4 places for it to bond, essentially, and that's why it has 4 bonds. So we are good there, okay? So 4 atomic orbitals. What's next, though, is that we also need to figure out our LGOs, and in which case there's 2, 4, 6, 8. So that's 8 LGOs that are capable. And now we have to figure out the irreducible positioning, and we have to draw the phasing. So in order to do this, what we're going to do is we're going to deal with the phasing where it's just this, where it's just the sigma bonds. So the sigma bonds, how that's going to look is on this axis, ZYX, we're going to have this. Okay, that's our shape. And what we want is to find the irreducibles of this. And the irreducibles is going to be D2H. Oh, actually, so what we're going to call this is R sigma P. It's not a, this is not actually an R. It's irreducible state. Anyways, R sigma P. Let's see if I can bring this up a little bit. No, down. Okay. And what we want is the very top of this, all the symmetry operations that we're going to do to this for our D2H. And where we're going to get that is from our little handy sheet that we're always going to have that has all our symmetry operations. And our symmetry operations are all these. So these are all the things that it's capable of doing. So if we do that, we're going to see that it's E, C2Z, C2Y, C2X, I, sigma XY, sigma XZ, and sigma YZ. Okay? And what we're going to do is we're going to go through every operation and figure out how much it affects it. And what we're going to say is if it doesn't change the phasing, it gets, for both of these, it gets a 1. If it does change the phasing, like this becomes the opposite, like this becomes white and this becomes dark, then we get it a -1. And if it doesn't, if it moves the phasing at all, it gets 0. So E is the identity phasing, and the identity is that it doesn't change at all. There's nothing, like nothing can happen to it. That's the identity. So that means it automatically gets a 2 because these stay the same. Now C2Z, we talked about C2 before. And C2Z is we go to Z and we're going to rotate it, and since it's 2, 180. And if we rotate this 180, we're going to notice that this pretty much stays the same, so it gets a 2. A C2Y, if we rotate it around here, what's going to happen is that both the phases move, and therefore it gets a 0 because, well, they move like we just described. This one, C2X, right here, if we move it around like this, again, at 180 degrees, both these things change, we get a 0. For an inversion point, what we do is we check it. If we invert across here, the atoms are going to move. It's going to get a 0. Why? This sigma symbol is not the same. 1 second. This sigma symbol, XY, and this is XZ, and this is sigma YZ. Essentially what this means is that on the XY plane, like right here, if you were to mirror it across, what would happen? And if you look at it, you're going to get, well, the same thing. So it's a 2. If you mirror over XZ, this doesn't change at all, so you get a 2. And over YZ, again, it doesn't change, so you get a 2. Now, we have to use the irreducibles, this, to see what atoms we get and how we're going to use that. So what I'm going to do is I'm going to flip the page, set my boundaries, and I'm going to re-put the thing on and show it. Okay. Okay, and then we're going to say R sigma P, and we're going to say D to infinity, or D2H, sorry, identity, C2Z, C2X, C2Y. I mixed them up, but that's okay, they're all 0 anyways. I, sigma XY, sigma YZ, and sigma XZ. And I mixed those up too, but that's also okay because, again, those are all 2s. So I'm just going to draw this out real quick. Okay, so we have 2, 2, 0, 0, 0, 2, 2, 2. Okay, and in order to do this, in order to figure out how much contribution each symmetry affects this, and like what contribution is happening, what we're going to do is we're going to take our sheet and we're going to take this, okay? And we have a handy equation, and I don't really feel like writing out the equation, I just remember the process. So what we're going to do is we're going to say H is going to equal the square of each number in this column. So that's all added together. So the square of 1 is 1, and the square of 1 is 1. So 1, 2, 3, 4, 5, 6, 7, 8. We get 1 over 8. Okay? Or we're saying it is 8, actually. And the equation that we're going to work with is that it's kind of difficult, but essentially what you do is you say AG is equal to 1 over 8. And what you do is you take this times the coefficient at the top times the number in the column. And you do that and you add it all up and see what you get. And so right from the beginning, what's going to happen is we're going to get 2 times 1 times 1 plus 2 times 1 times 1. And these are all zeros, so I'm going to leave it out because 0 times anything is 0. 2 times 1 times 1. I know it gets tedious. And 2 times 1, 1. And 2 times 1, 1. And now that we have that, we can figure this out. So we got 2, 4, 6, 8. Let me think. 1, 2, 3, 4, 5, 10. I feel like I messed up somewhere. I just can't see where. Oh, you know what? This, where is it? X, Y. Y is easy. X, Y is -2. Nope. Yes, X, Y is -2. That is actually an important mistake that I made, and I apologize. Okay, because what this is going to give us is 8 over 8, which is 1 symmetry. Okay, and we have to do this for every one. And that takes a while because, like, if you look here, there's a shit ton. Yeah. So instead of doing that, I already know that there's 1 AG and 1 B1EU. 1 B1U. So in total, there's 1 AG plus 1 B1EU. And then we want to visualize this LGO. And in order to do that, what we're going to do is we have to take these irreducibles and we have to normalize them and use this thing called SALC. It's an acronym. I can't remember the exact acronym, but that's essentially it. And what we do is we take this and we put it like this. We go like this. AG is equivalent to the identity. So what we're doing is now each of these, I'm going to quickly draw this out real quick. Made this Z, I'm pretty sure, Y, X. So, and then here it is. So each of these is an oxygen, right? Oxygen 1, oxygen 2, because they're both on the sides of, well, carbon. So what we're going to do is we're going to take one oxygen, we're going to figure what happens when we use these symmetry operations on it. So, and it does also have another equation. It's somewhat like this, not entirely, but it is. And so what we do is we take all these and we take all these. So E, C2, Z, C2X. Now these ones won't have zeros in front of them, and I'm going to show you why in a second. C2x, I just got to make sure I have enough room, C2y, I, sigma xy, sigma yz, and sigma xz. Okay, so what you're going to do, and what I'm going to do later on, is you're going to go to what the symmetry operations we found. So we found AG and 1B1U. So for the very first one, for AG, we take every number in it and we put it there. So we get 1, 1, 1, 1, 1, 1, 1, 1. So there's, all these are ones. And then we think about what happens to one of the oxygens. I'm going to pick this oxygen. So if the identity happens, it stays the same. So it's just 101. Or sorry, there's no sigma. 101. C2 happens. Well, when you spin around the z-axis, it stays 01. So we get 101, and we add it. For C2, let's see, X. C2X, what happens is when this flips, it becomes O2. Like when this goes around, it becomes O2. So we put plus 1, O2. Stays in the same phase, so we don't change it. Doesn't become negative. C2Y, same thing. If we rotate it like this way, this will rotate around and hit this one and become O2. So again, we get plus 1, O2. For the identity matrix, it goes across and it becomes, it'll go across like this, or whatever way you decide to invert, and it will become O2 again. So again, we get plus O2. Over XY, O1 becomes O2. And then over YZ, it stays the same, O1. And over XZ, where it's like this, where the plane is here and it mirrors itself, it becomes O1. So what we're going to end up with is 4 O1s plus 4 O2s. And there's no explanation. We get rid of the coefficient, so we pull the 4's out. You get O1 plus O2 by coefficient. And then we normalize, and that is we multiply this by the amount of coefficients is in here squared, square rooted, well, over itself. So this is 1 over the square root of 2. So what we got is 1 over the square root of 2, O1 plus O2. And what that says is that for this LGO, like for the AG LGO, it looks like this. And this LGO, if you try to put it with another P block, it will actually be out of phase. So like that one will not work. But if we go to the next one, which is B1U, and we do the same thing. We get the E. So I'm not going to actually write down the E and everything. I'm just going to put down the front coefficients that we're going to use. So what we have is 1, 1, negative 1, negative 1, negative 1, negative 1, 1, and 1. I will put it on top though, just so that we have the visual. Z2Z, C2X, C2Y, the inversion. Oh, wait. Okay, yeah, that's good. The inversion over XY, over YZ, and over XZ. Okay. So if we do this again, we still have to figure out the oxygen. So what we're going to get is when the identity happens, you're actually going to get pretty much the same results up to here, because like everything has to happen the same way, except for the only difference is you get these negative coefficients out front. So what you're going to end up with is oxygen 1 plus oxygen 1, I believe. Let's see. Yeah. minus oxygen 2 minus oxygen 2 minus oxygen 2 minus oxygen 2 plus oxygen 1 plus oxygen 1. And you're going to end up 4 oxygen 1s minus 4 oxygen 2. And you're probably wondering, like, well, like, again, we still have to get rid of this coefficient, so we do. And again, this would have to be 1 over 2. So you get oxygen over times the square root of 2. And what this represents is that negative is that they're out of phase. So what we're going to have is this. Like, I shouldn't say out of phase. I won't know how to describe that better, though. They're similar in the shape and size. They look like this instead of looking like this. Okay? Now, we described the p orbitals, and two p orbitals and the s orbital, and then blah, blah, blah. And now we have to, once again, I'm just going to get the light so we have it. It's starting to get dark in here. Okay, the next thing is that we have to figure out the rest of the p orbitals. Okay. And then the next participating orbitals are this. We have we'll make this Z, Z, Y, Y, X. What we're going to have is this. Okay? And again, we have to figure out, first we have to figure out the irreducibles. So how we do that again is we're going to say this. Px. No, that's Py, sorry. Going upwards, Py. And we're going to put the E, the C2Z, C2X, C2Y, I, sigma XY, sigma XZ, and sigma YZ. Okay. I just went through it. That's okay. And then we'll also have another one for this one, which is px. And the px is because it's in the px in the x-plane. And that's because they're p orbitals. So for the py, there's two of them. They don't change. 2. C2z, if I rotate this, what happens? Well, if I rotate this, these phases actually change, and that's where I get a -2. C2x, if I rotate it around the x-axis right here, like this, they'll actually move, so they're actually 0. C2y, again, they'll move, 0. Inverted over the I, it moves, 0. XY, over the XY plane, which is right here, they move. Oh no, yes, they do move, so 0. Something's wrong with that, actually. Oh, I know where I messed up. That's not what I did. It's just that. You'll still get an 8, and the answers will still be the same. I just messed that up. Okay. Anyways, XZ. So we have sigma XZ, and we flip it over the XZ mirror. And what's going to happen here is that they're going to switch phases, so we get -2. Over the YZ, nothing happens over that, so we get 2, regular 2. We go through RDX real quickly. Again, nothing changes to 2. Or rotate around the C2Z, you'll get -2 again because the phases change. Right? This goes this way, essentially. C2X, we rotate, the phases move, that's a 0. C2Y, the phases move, that's a 0. Inversion, again, it gets inverted and moves the atom, 0. Mirror over the XY plane. XY. If I mirror over here, what happens? They move, that's a 0. XZ. XZ here does not change these at all. It keeps them the same, so this time it's a +2. And for this one, when it mirrors over the YZ, though, we get a -2. And so what we've ended up here is that these two values have kind of switched. This is a -2 and a 2, and a 2 and a -2, and that's how we're going to get our two different irreducibles. Now, I've already shown you how to do it, so I'm not going to do it again. But essentially, what we're going to end up with is we're going to end up with, for this one, RP at Y, we're going to get B3G plus B2U. And for RPX, we're going to get B2G plus B3U. And we're actually just going to go over only one of these sets one more time, like for visual's sake. We're not going to go through both of them, but how it's going to work is, again, we have the identity 1, or we have the identity, the C2Z, C2X, C2Y, I, sigma XY, sigma XZ, and sigma YZ. And the irreducible, and then again we put the coefficients up front, and we do it for, what we're doing it for is B2U right here. B2U. I'm sorry for how blurry it is, my webcam's not the best. Anyways, this is B2U. Maybe I should use a pen instead. Let's use, how does green show up? Green's not bad. Okay, B2U. And again, we'll have E, C2Z. Oh, I already did it actually, but I'll do it again. C2Y, C2X. I mix these around, so I'm going to put a little arrow here. I, sigma XY, XZ, and sigma YZ. Okay. What we're going to do is, again, we're going to take the B2U column, and that's what we're going to use for our numbers. And for that, we get 1, -1, 1, -1, -1. Those are switched, yep. 1, -1, and 1. And if you add these together, again, we're going to use our oxygen, and what the pattern should be is oxygen. Oxygen 1, oxygen 1, oxygen 2, oxygen 2, because this is oxygen 1, this is oxygen 2, oxygen 2, oxygen 2, oxygen 1. And what that's going to have, again, is we're going to end up, oh, and this is important because there's negatives here, that some of these will actually get a -1 when it switches around because of the phase change. So this changes the phase 1 of oxygen, so you actually get a -1 in front of a -1. A -1 here in front of a -1. Another -1 here in front of a -1, and another -1 here in front of -1. And what you'll actually get is O1 plus O2 over the square root of 2. And what that means is that for this one, this symmetry, you get, not that, this. For the other one, you're gonna, it's gonna go through the same thing, blah blah blah, B3G, except the B3G is going to look like this. And it's going to be 1 over the square root of 2 equaling O1 minus O2. And that's the answer you get for that one. And that is what you learned today on April 2020.